Hypothesis testing, practice test number 4, will prepare you for test number 4. Test number 4, as a reminder, will include Chapter 8, hypothesis testing, and Chapter 4, probability. Question number 1. The health of the bear population in Yellowstone National Park is monitored by periodic measurements taken from anesthetized bears. A sample of 64 bears has a mean weight of 182.9 pounds. Assuming that sigma is known to be 121.8 pounds, use alpha equals 5% to test the claim that the mean of all such bear weights is at most 100.5 pounds. Let's take a look at the questions. What is the claim? What's the critical value? What is the test statistic? What is the decision? If you notice, I did not specifically ask for the critical value or the p-value. That means it's really up to us to decide if we would like to use traditional or p-value. I will set this problem up with both methods and then answer the questions. The claim is stated at the very end. Test the claim that the population mean, and that'll be mu, of all such bear weights is at most 100.5 pounds. At most as a symbol is less than or equal to. Therefore, there is your claim. The population mean of all such bear weights is at most 100.5 pounds. To test this claim, they take a sample of 64 bears, and their mean weight, X bar, is 182.9 pounds. Assuming sigma, standard deviation of the population, is 121.8 pounds, test this claim. This will be a z-test for the true mean, and the reason it's a z-test, either sigma is known or n is at least 30. Sigma is known and n is at least 30. I only need to satisfy one condition, but I did satisfy both. Therefore, it is a z-test for the mean. I will focus on the traditional method first. If you go to your possibilities for setup and you look for the symbol in your claim at most, less than or equal to, you know that that has to be part of the null, and the alternative is greater than. In this problem, the claim is the null hypothesis, which says at most. Once again, as a reminder, your sheet that is attached to your test, you look for less than or equal to, which means at most, therefore your alternative is greater than. So this is a right-tailed z-test for the mean. Not only is it a z-test, but it's right-tailed z-test for the true population mean. Question number 2, or step number 2 of the traditional method, is to find the one and only critical value. So I'm drawing the z-axis and I'm shading that right tail, and that's all of the alpha of 5%. So you're looking for this positive z to indicate your critical value. I think you know by now that if this is the 2-page z-table, then you have to look up the area below the unknown z, which is that area of 95%. If you look up that area in the 2-page z-table, you will see that it falls halfway between two areas. And the textbook says to go with the larger z-score that's going to give you the larger absolute value. And that will be 1.65. Therefore, your critical value is a positive 1.65. If you do invert norm and you put in the area below the unknown positive z, again you'll put in 0.95 and you will get 1.64. I will show you invert norm now. Second variables, number 3. 0.95 is below it. Z distribution, the mean is 0, the standard deviation is 1, and paste. 1.64 to 2 places accurately. Now I will show you the 2-page Z table if we look up an area of 95%. If you go to the 2-page Z table to look up an area of 95%, you will find that that area falls halfway between 0.9495, 0.9505, and it's here in the middle. And if you work your way out, it's 1.64 here. If you work your way out, it's 1.65 here. So we go with the larger of those two Z-scores in terms of absolute value. So we're here, 1.65. That 1.65 marks your rejection region. Step number 3 is the test statistic. The test statistic is Z equals X bar minus your claim divided by sigma over the square root of n. X bar is 182.9, the claim is 100.5, standard deviation was 121.8, and the sample size was 64. You will round this test statistic to 2 places accurately since it is a type of Z-score from the Z table. 182.9 minus 100.5 equals, divided by parentheses 121.8 divided by the square root of 64, arrow out from underneath the radical and parentheses. Enter. 5.41 to 2 places accurately. You could also go to Stat and Test and Z-Test, number 1. The claim is 100.5. The standard deviation is 121.8. Sample mean is 182.9 and sample size is 64. The alternative is greater than, pointing to the right because it's a right-tailed Z-test. And calculate. Enter. The test statistic is a 5.41 and the p-value 3.1207 times 10 to the negative 8. And I'll write that p-value out in just a moment when we talk about the p-value method. But for now, we're still in traditional mode. And I will put the 5.41 where it should fall in the picture. Therefore, step 4, reject the null hypothesis. And that says that mu is less than or equal to 100.5. And that just so happens to be your claim. So what is this going to mean in terms of summary? Our claim is the null that says at most. And our decision is to reject that null statement. Therefore, there is enough evidence to reject the claim that it is at most 100.5 pounds. There is enough evidence to reject the claim. And I will write that out. There is enough evidence to reject the claim that mu is less than or equal to 100.5 pounds. Remember, since we rejected the null, there's still the possibility of a type 1 error, rejecting the null when it could be true. So rejecting something that's true is a mistake, but we'll never know that. But there's still the possibility that we committed a type 1 error in this problem. Let's answer the questions before I show you the p-value method. First question is, what is the claim? And I'll just come here. The claim is the null, and it says less than or equal to. So let's look for that here. And that is D. What is the critical value? We did that here. The critical value is 1.65, and that is C. What is the test statistic or calculated value? We did that here, and it's 5.41. What is the decision? Reject the null. There is enough evidence to reject the claim that the population mean of all such bear weights is at most 100.5 pounds. The answer is D, and we answered that here in question or steps 4 and 5. That's what I mean by read the problem, see what type of questions they're asking, and decide upon a method. The best method to show would be traditional because it does ask for a critical value. Once you go through all the steps, it's very easy to come back to the problem and just give the answers. So D, C, A, and D. D, C, A, and D. I do wish to find the p-value for this particular problem so that if we did go through the p-value method, we would be able to make our decision in summary. So we would find the p-value from the z-table, and we would have to use our test statistic to find it. If you remember, the test statistic z was a 5.41. We take our z-axis, our bell-shaped curve, and we put our 5.41 on the axis. That's a really large z-score test statistic. Since this is a right-tailed z-test, we only have to find this area in the right tail designated by the test statistic of 5.41, and this area is the p-value for this problem. We have a little situation here. If you notice with the two-page z-table, the largest z-score is 3.49, and it says at the footnote, for z-values greater than 3.49, use an area of 0.9999 below it. So the area below 5.41, we're going to use 0.9999. That is this area. That means the p-value is 1 minus 0.9999, which is 0.0001. Therefore, the p-value for this problem is 0.0001 by hand. If you remember from the calculator, when you go to stat and test and z-test, it turned out to be 3.1207496 times 10 to the negative 8. So that's 0.123456731207496 if you move the decimal to the left 8 places. And that's the calculator p-value. Decision time, alpha, box, p-value. I'm going to use the one that I got by hand, but it really doesn't matter. And alpha was given to be 5%. I think you can see that alpha is larger. And when alpha is larger than the p-value, you reject the null statement. And the null statement was our claim that mu is at most 100.5. So therefore we have the same decision and we have the same summary statement. If alpha is larger than p-value, reject the null statement. That's where that's coming from. So you would need to compare those. And so if you wanted to do the same problem with the p-value method, or if I ask you for the p-value by hand, you would give me 0.0001. The one by calculator is more accurate, of course, because It's not using a table, but it's very, very small. Alpha is definitely larger. So reject the null statement. Again, we have the decision and we have the summary. There is enough evidence to reject the claim. That concludes our very first whole hypothesis testing problem on this practice test. Let's move on. Problems 5 through 8 deal with raw data. And it says the dean of the university claims that the mean number of classroom hours per week for full-time faculty is exactly 12.1 hours. As a member of the student council, you want to test this claim. A random sample of the number of classroom hours for 8 full-time faculty for 1 week is listed below. At alpha equals 1%, test the university's claim. And the claim is that the mean number of classroom hours per week for full-time faculty is 12.1 hours. This is what we are testing. Let's take a look at the questions. What is the mean of the sample and the standard deviation of the sample? Oh, this is raw data. What is the test statistic? Okay. What is the p-value interval? We must have to do the p-value method. And then what is the decision? Not only p-value method, because it's asking for p-value interval, it's probably, most definitely, a t-test for the mean. Let's take a closer look. Again, the first thing to do is to write down the claim. The claim from the university and the student council is testing this claim that the mean number of classroom hours per week for full-time faculty is, so the mean is 12.1 hours. Therefore, mu is equal to 12.1. To test this claim, the student council takes a random sample of 8 full-time faculty, so n is 8, and alpha is 1% to test this claim. If you notice, question 5 does ask for x bar, and it asks for the sample standard deviation. That would mean that this is indeed a t-test for the mean. That is when sigma is unknown, and at the very same time n is less than 30. Both conditions must be satisfied. Sigma, population standard deviation, is not given anywhere. It is implied that we find S, sample standard deviation. And your sample size is only 8. You should plug this data into the calculator, but I'm not going to do that. I think we've done that a lot with these Tegrity videos and in class. But I will tell you that when you take this raw data, and I do say to round to 3 decimal places, technically, since this is raw data, and the raw data values are given to the nearest tenth, we should round to 1 additional decimal place. That would be the nearest hundredths. But notice that I do say specifically to round to 3 decimal places. Therefore, that means that I am not necessarily going according to the rounding rules stated in Chapter 3. I decided to round differently, so I told you specifically to round to 3 places. And that's E. 10.05 for the sample mean, and my sample standard deviation is 2.485. And I'll write both of those down. Please verify with this raw data that you received these 2 values, and again round to 3 decimal places as stated. I am going to perform the p-value method with this problem. Since it says equal to 12.1, that has to be the null, and the alternative has to be not equal to. The claim is therefore the null hypothesis. Again, when you go to your sheet and you're looking for symbols that represent your claim equal to, you are here. The null is equal to, the alternative is not equal to. So it's a two-tailed t-test for the mean. The next step of this two-tailed t-test, and you may want to write that down, two-tailed t-test. Means you use the t-table. Since this is p-value method, you will need to find your test statistic, and that's x bar minus the claim, s over the square root of n. That is 10.05 minus my claim of 12.1 divided by my sample standard deviation, and that was rounded to 3 places, divided by the square root of 8. When you calculate that value, it will look like this. Negative 2.333. And I rounded to 3 places because in the t-table values are given to 3 places. If you go to stat and test and t-test, which is number 2, you will have that your claim is 12.1. Your sample mean is 10.05. Your sample standard deviation 2.485. Your sample size 8, and it's 2-tailed, so no longer equal to is the alternative, and then calculate. Remember, I calculated from raw data the sample mean and the sample standard deviation. The test statistic t is negative 2.333, and the p-value is 0.0524. But we need to give a p-value interval eventually. That's the next step of the p-value interval. A p-value method is the p-value interval, since this is a t-test. You will remember that your alpha is 0.01 and it's 2-tailed. That's necessary to know. And your degrees of freedom would be 7. So you want to go to your t-table, and you want to block off row 7 and look up that alpha. Excuse me. I think I'm thinking about critical values. Don't need alpha for p-value. I need the test statistic. The test statistic is needed. The knowledge that it's 2-tailed is needed, and your degrees of freedom. Sorry about that. Remember, alpha determines critical values with the traditional method, but the test statistic determines the p-value interval with the p-value method. Row 7. You look across the row and you find the 2 values that bound the absolute value of your test statistic. And that will be these 2 values. But you take the absolute value of negative 2.333, and that's a positive 2.333. Then you go to the top of the table, and you stop here at 2-tailed alpha because it's a 2-tailed t-test. Cross fingers. Your p-value interval is between 0.05 and 0.1. 0.05 and 0.1. Row 7. Find the 2 values that bound the absolute value of your test statistic. Our test statistic was negative, so we need to make it a positive. And go to the appropriate row, 2-tailed, cross fingers. Therefore, p-value interval would be 0.05 less than p-value less than 0.10. And that's using the test statistic. The p-value from the calculator is 0.0524. And notice how that does indeed fall in your p-value interval. The 0.0524. It's a little bit larger than 0.05. Now, decision time. Alpha compared to any possible p-value, and you could use the specific p-value if that helps. Alpha was given to be 0.01, But our p-value is between 0.05 and 0.1. Or you could use the calculator p-value. Alpha is smaller. Therefore, do not reject the null hypothesis. And that said that mu was equal to 12.1. That's also our claim. So do not reject the null, and the null is our claim. There is not enough evidence to reject the claim that the mean number of hours worked by full-time faculty is exactly 12.1. There's not enough evidence to reject the claim that mu is equal to 12.1. Now, let's look at these questions. We already answered 5. What is the test statistic? Negative 2.333. We found that here. Step 2. What is the p-value interval? 0.05 to 0.1. We found that here, step 3. What's the decision? Do not reject the null. There is not enough evidence to reject the claim that the mean number of classroom hours per week for full-time faculty is 12.1 hours. So the answer is D. One final thing you may be interested in is finding possible critical values if you wanted to perform this same test. What you would do is you would have two critical values. You draw your t-axis, shade your left tail, shade the right. You're looking for the plus and minus t. You would use your alpha of 1% and your degrees of freedom of 7 and go to your t-table. Look up your alpha that's given to you in the two-tail alpha row because it's a two-tail t-test. And here's the 0.01 and here's row 7. Your two fingers meet at plus and minus 3.499. And those would be your two critical values which determine your two rejection regions. 3.499 plus and minus. And I'll write that in the picture. So if I did ask for critical values, that's what you would give me. And if you notice, your test statistic of negative 2.33 falls here. Therefore, do not reject the null by the traditional method. Same decision. So if I ask for critical values, it's plus and minus 3.499. And that concludes the second problem on the practice test. And that was a t-test. Next problem. A local newspaper claims that at most 44% of households receiving magazine sweepstakes in the mail respond to them. An intensive study TV campaign was aired for 2 weeks prior to the mailing of Fantastic Fantasy Sweepstakes offering. In a random sample of 300 households, it was found that only 156 did respond to the sweepstakes mailing. Test the claim at alpha equals 0.025. When you read this problem, I don't care how many times you read it, you do not see the word mean or average or variance or standard deviation, and you see some percentages. This is about proportion testing. Again, a local newspaper claims that at most 44% of households receiving magazine sweepstakes in the mail respond to them. In an intensive study TV campaign, it was aired for 2 weeks prior to the mailing of the Fantastic Fantasy Sweepstakes offering. In a random sample of 300 households, that's your N, it was found that X, 156, did respond to the sweepstakes mailing. That's going to give you your p-hat. Alpha is 0.025. Let's look at our questions. What is the claim? What's the p-value? What is the decision? Obviously, this is probably the p-value method since they do ask for a p-value. With this claim, basically they're saying that the proportion is at most 44%. A local newspaper claims that at most 44% of households receiving magazine sweepstakes in the mail respond to them. Therefore, P is less than or equal to 0.44. To test this claim, they take a sample of 300 households and find that out of that 300, 156 people respond to the sweepstakes mailing. Alpha is 0.025. We will go through the steps of the p-value method for this problem. First step is the setup. Since it's less than or equal to, which means at most, that has to be part of the null, and the alternative is greater than. The claim is the null hypothesis. Again, you're looking for at most, which is a symbol. And once you know your symbol at most, you're coming here. Less than or equal to means at most. That's the null. Greater than is the alternative. It's a right-tailed z-test for true population proportion. So replace the mu that you see, this mu, with p, population proportion. And you'll be using the z-table. The next thing you may want to do is p-hat. It is x over n, or 156 out of 300. The textbook says if that's not a nice number to round to 3 places accurately, and it is a very nice number of 0.52. Also, your Q is 1 minus your claim P, which is 1 minus 0.44, and 1 minus 44% is 56%. You need to know P and Q. P is the claim of 44%, therefore Q is 56%. Step 2 of p-value method is the test statistic. P hat minus P over the square root of P times Q over N. That's 0.52 minus 0.44, which is my claim, over the square root of my claim, 0.44 times Q, 0.56, over N, which is 300. You'll round to 2 places accurately because it's a type of z-score. 0.52 minus 0.44 divided by square root, parentheses, 0.44 times 0.56, close parentheses, divided by 300, and arrow out from underneath the radical. Press enter. .79 is your test statistic. Also, if you go to stat and test and number 5, one prop z-test, the claim is at most 44%. The X is 156 and your sample size is 300. This is a right-tailed proportion z-test, so let it blink on greater than 0.44. That's your alternative hypothesis. And then calculate. See, your alternative is greater than, so you should click on greater than here. The test statistic is 2.79, and the p-value by calculator is 0.0026 by calculator. I want to find the p-value by hand. P-value is the next step of the p-value method. You take your standard normal distribution and you put your test statistic where it should fall. If you find this area in the right tail, which is determined by your test statistic of 2.79, you have your p-value. This is where you could do normal CDF, and you put in negative E99, comma 2.79. Excuse me, made a mistake there. You want the area below it, so it's normal CDF. 2.79, comma, positive E99 to positive infinity. And that'll give you the area in the right tail. So second variables, number 2, 2.79 is the lower, E99 is the upper, and it's the Z distribution, so you paste again or enter, 0.0026. Let's check out the table. If we check out our Z table and we look up a Z score of 2.79, we are here with the 2.7 and then 0.09, 0.9974. That's the area below your test statistic, 2.79, 0.9974. That's this. Therefore, this p-value is 1 minus 0.9974. And that should give you 0.0026. Regardless of how you do it, by hand, by calculator, by table, normal CDF, you get 0.0026 for your final answer for p-value by hand and everything else. Calculator and by hand agree. Alpha p-value, comparison time. Alpha was given to be 0.025 and your p-value is 0.0026. 0.025 is larger than 0.0026, so greater than or equal to, reject the null. And the null statement says P is at most 44%. It's also our claim. So reject the null, which is our claim. What does that mean about the claim? What is the summary statement? Going to the diagram, the claim is the null, reject the null. There is enough evidence to reject the claim that P is at most 44%. There is enough evidence to reject the claim that the proportion of people who respond to sweepstakes, the mailing, is at most 44%. There is enough evidence to reject the claim. Let's answer these questions on the worksheet. First question was, what was the claim? And we got that here. It's the null. P is less than or equal to 0.44. So it's answer C. What is the p-value? The answer is D. We found that by our test statistic, we found our p-value. What's the decision? Reject the null. There is enough evidence to reject the claim that the level of response to the Fantastic Fantasy Sweepstakes is at most 44%. So the answer is A. If you wish to find the critical values for this problem, or critical value, since it is a right-tailed test, you would draw your Z distribution, shade the right tail, and you're looking for this Z. This is all of your alpha of 0.025. So you would want to do invert the norm on this. But area below it, which is 1 minus 0.025, which is 0.975, and then paste. And you get 1.96 for your critical value. So the area below it is 0.9750. If you go to your 2-page Z table and you try to look up the area below it, 0.9750, here you are exactly in the table, and when you work your way out to 1.9 and up to 0.06, is still a critical value of a positive 1.96. And that 1.96 marks the rejection region. If you remember, our test statistic was 2.79, and 2.79 falls in that rejection region. So again, if you give the traditional method and I ask for the critical value, 1.96, you still reject the null hypothesis because the test statistic falls in the rejection region. 1.96 is your critical value, positive. The only one because it's a right tail proportion z-test. And that concludes the third whole problem there in your practice test. Questions number 12 and 13 and 14 and 15 and 16. I noticed that there is not a chi-square test represented on this practice test. Therefore, that means that you definitely need to study those worksheets that I gave you from Section 8.5 on chi-square testing. Okay, I do not know how to pronounce the name. I'm just going to say B was trying to decide whether to use a new racing wax for cross-country skis. He decided that the wax would be worth the price if he could average less than 55 seconds on a course he knew well. So he tested the wax by racing on the course 8 different times. His average time was 53.1 seconds with a standard deviation of 7 seconds. What is the hypothesis being tested? What type of test is needed? Calculate the test statistic. What is the decision? Okay. Again, we have to examine the problem, and we need to write down the claim. So we have this young man named B. He was trying to decide whether to use a new racing wax. He decided that his wax would be worth the price. He was going to buy the wax if he could average less than 55 seconds on a course. So what he's testing is that the average is less than 55 seconds. So mu less than 55 is the claim or what he wishes to test. In order to test this wax and see if he would like to buy it, he decided to go and race on the course 8 times. And his average time during those 8 races was 53.1 seconds with a standard deviation of 7 seconds. So that's S, because with that sample of 8 races, his average time was 53.1, and that standard deviation of that sample was 7 seconds. So that's S. Therefore, this is a t-test for the mean. Step number 1 is the setup. Mu and mu. Less than would have to be the alternative, and greater than or equal to would have to be the null. The claim is that he's testing if he can average less than 55 seconds. So this is a left-tailed t-test for the mean. Left-tailed. And question 12, what or which hypothesis should he test? It's A. So less than is in the alternative, and greater than or equal to is in the null statement. So it's A, a left-tailed t-test. 13, it's a t-test because the sample size is small, less than 30, and at the very same time, sigma, population standard deviation, was not given. It only gave sample standard deviation for 7 seconds. For his sample of 8 races, the standard deviation of those 8 races was 7 seconds, and the sample mean was 53.1. So it's a t-test because both conditions are satisfied. Question number 14, what's the test statistic? So it's going to be completely up to us which method that we would like to use for this problem. I'll do traditional first. If it's the traditional method and it's a t-test, you shade the left tail, and you're looking for this negative t to be your critical value. You would go to degrees of freedom, row 7, and look up your alpha, which is given to you. And let's see, alpha is 0.01. And we find that out here in question 15. I'm going to the t-table. Row 7 and alpha. We go to the one-tail alpha row to look up our alpha because this was a left-tailed t-test. And two fingers meet at 2.998, but we need to make that a negative 2.998 as our critical value because this is a left-tailed t-test. 0.01 and row 7, negative 2.998. And that goes here. Step 3 is the test statistic, and that's x bar minus mu s over the square root of n. 53.1 minus the claim of 55 divided by s, which is 7, divided by the square root of n. And the test statistic is going to be enter, negative 0.768. If you go to stat and test, and t-test, your claim is 55, less than 55. Your sample mean is 53.1. Sample standard deviation is 7. Sample size is 8 races. And it's a left-tailed t-test, so less than is the alternative, and calculate. Enter. The test statistic is a negative 0.768, and your p-value is 0.2339 specifically. Put your test statistic in the picture. Negative 0.768. is larger than negative 2.998. Therefore, do not reject the null hypothesis that says mu is at least 55 seconds, greater than or equal to 55 seconds. Unfortunately, that means that since the claim is the alternative, there's not enough evidence to support B's claim. He's not buying that wax, probably. There is not enough evidence to support the claim from B, or what he's testing, that it's less than 55 seconds. If you're not rejecting the null statement, then you cannot support the claim statement. But you could go to your diagram and put your finger on the fact that your claim is the alternative and you decided to not reject the null, and it will lead you to the box that says there's not enough evidence to support his claim. So he probably will not buy the wax because it's just not going to shave time off of his race. He wanted it to be less than 55 seconds. If you go here, now the test statistic said to round to 2 decimal places. We got a negative 0.768. To 2 places it is a negative 0.77. Do not reject the null hypothesis. We did that with the traditional method. Just so you know, if you find the p-value interval for this problem, because this is a t-test, you will block off row 7 and you will look across to find the absolute value of your test statistic, because our test statistic was a negative 0.768. And we want to find the 2 values that bound the absolute value of our test statistic. And that would be this first value here and here. Absolute value of negative 0.768 is a positive 0.768. Go to the top, and since it's a one-tail test, stop here at 0.25 and 0.1 and cross fingers. So your p-value is between 0.1, which is smaller, and 0.25, which is larger. So 0.1 comes first. Again, row 7, degrees of freedom. Find the two values that encompass the absolute value of your test statistic. Go to the appropriate row according to the type of test. It was left-tailed or one-tailed, and cross fingers. Therefore, the p-value interval for this problem was between 0.10 and 0.025. That means when you take your alpha box p-value, and the p-value by calculator, by the way, was given to be 0.2339, and you'll see that this p-value falls in that p-value interval that I'm asking for. The alpha was given to be 0.01, and therefore it's smaller. If alpha is less than p-value, do not reject the null hypothesis. Therefore, there is not enough evidence to support B's claim. Same decision, same summary. Alpha is smaller than the p-value from the calculator or any possible p-value in this interval, 0.1 to 0.25. And that concludes that fourth whole word problem here. The last one is either you know it or you don't type problem. Are the following statements valid? And H sub A is the same as H sub 1, so there's nothing wrong with that notation. HA is okay to use instead of H1. This is not because there are no parameters contained in these statements. I don't have mu equals 7 or mu does not equal 7. I do not have sigma equals 7 or sigma doesn't equal 7. I don't have a p here for proportion, a mu here for the mean, sigma squared for true variance, or sigma for true standard deviation. I don't know what parameter I'm testing. So this is not valid according to letter D. We don't see any parameters there. And we need to see our parameters. Again, the chi-square testing is not represented, so go according to the worksheets that I've given you in class and many other examples, and I think that you'll be great with the chi-square testing. I hope that this semester of Tegrity videos has been very helpful to you. I did this because I do care about my students, and I'm trying very hard to reach my students in any way possible. I try very hard to give you your lecture notes and give you as many examples as possible. So I'm hoping and praying those of you that have appreciated these Tegrity videos, I wish you the very best, and I'm hoping that you will receive the grade in the class that you're hoping for. And thank you again for a wonderful semester of Tegrity videos. God bless you and have a wonderful day.